Hello, everyone. This is Professor Cevat Yaman. I will be presenting bioremediation of toluene by bioaugmentation, biostimulation, and natural attenuation. That's the title of our presentation. And the other, my colleagues are Dr. Ismail, Anil, Professor Omer, Ayse, Yaman, and Aleem, Qureshi. This is the outline of my presentation, introduction, methodology, results, discussion, and conclusions. As you may know, contamination in a subsurface environment is a serious environmental problem. And the sources of the subsurface environment, when I say subsurface environment, I mean both subsurface soil and also groundwater. And the sources of subsurface contamination are petrol, diesel fuel, gasoline, underground storage tanks, transmission pipelines, and other non-petroleum related industries. So those are all causing subsurface contamination. And one of the available technologies to clean the subsurface environment is called bioremediation. In bioremediation, we use microorganisms to biodegrade organic contaminants. And in this situation, we talk about hydrocarbon. And if most of the time, subsurface soil contains some microorganisms, but sometimes the amount of microorganisms is not sufficient. So in that situation, you have to add some microorganisms externally. And this process is called bioaugmentation. And sometimes the nutrients in the soil or groundwater is not sufficient, then you have to add some nutrients. And this process is called biostimulation. And you can, if the groundwater is contaminated, you can pump and treat on the surface by biological or chemical processes. And also you can also treat this groundwater in situ by using different technologies. And one of the most available and effective technologies to treat groundwater in situ is called permeable reactive barriers. Permeable reactive barriers, they are filled with reactive materials, and these permeable reactive barriers, they must be permeable than their surrounding aquifer material. And when we compare with pump and treat systems, these PRBs are very efficient. They are very cheap compared to pump and treat systems. And there is no continuous energy input. And also the other benefit of PRB is that there is always a possibility to replace the PRB material. And in the literature, there are two types of permeable reactive barriers. One is continuous PRB, and the other one is funnel and gate PRB, as you can see in the figures. And the main mechanisms in permeable reactive barriers to remove the pollutants are degradation, precipitation, and sorption. So those are the mechanisms to eliminate contaminants in the subsurface by using PRBs. In our study, we selected toluene as the contaminant. The reason why we chose toluene is because toluene is one of the BTEX compounds, and BTEX is the major compound in gasoline. And toluene is also found in other paint pigments and solvents, in adhesives, metal cleaners, and paints. So toluene is a very common compound found in the industries, and it's one of the most common contaminants in the subsurface environment as well. The specific objective of our study was we investigated the toluene biodegradation efficiency in a freshly contaminated water by using bioaugmentation and biostimulation. We also used another reactor as a natural attenuation or a control reactor for comparison. Let's move to methodology. This is the configuration of PRBs in our study. The dimensions were 60 centimeter height and 10 centimeters diameter. And these two reactors are filled with sand and gravel. And reactor 1 was inoculated with microorganisms, bacteria, and also nutrients. But reactor 2 was not inoculated with bacteria and was not added any nutrients. But for both reactors, we added toluene, and the influent toluene concentration was 5 ppm, 5 milligram per liter. And and we use a peristaltic pump to feed these reactors at a flow rate of 1 milliliter per minute. And the reactors were operated as upflow reactors. And this table shows the reactive filler materials in these both permeable reactive barriers. And we had two different reactive materials, silica sand and silica gravel. And this table shows the diameters of silica sand and silica gravel that we used in our study. And also the table shows different characteristics of these filler materials in the PRBs, like acid solubility, bulk density, specific gravity, and so on. To analyze toluene, we use a HPLC chromatograph equipped with a UV detector. Let's move to the results. So first we did a permeability test or hydroconductivity test. And the method that we use to determine hydroconductivity is called falling head permeability test. This is the formulation that we use in this hydroconductivity test. And this is the results of hydroconductivity tests for reactor 1. The hydroconductivity was 0.779 centimeter per second, and for reactor 2, 0.766 centimeter per second. As you can see, the hydroconductivity values were similar in both reactors. We also determined pore volume and porosity in both reactors. Both reactors had a reactor volume of 4,710 cubic centimeters. Pore volume in reactor 1 was 1.06 liter, and porosity was 22.5%. And in reactor 2, pore volume was 1.15 liters and porosity was 24.4%. As you can see, both pore volumes and porosity values were similar in both reactors. And also hydraulic residence times were 14.58 hours in reactor 1 and 15.97 hours in reactor 2. Again, the hydraulic residence times were similar in both reactors. We also determined the oxygen requirement for reactor 1 only, because in reactor 2 we did not give any oxygen to reactor 2. We provided oxygen in reactor 1 only. And based on the stoichiometric reaction, it was determined that 15.6 milligram of oxygen is required to biodegrade 5 ppm toluene. And this table shows the nutrient, bacteria, and oxygen requirements for reactor 1 only. Again, we did not add any nutrients or bacteria to reactor 2. We added only to reactor 1. So this table shows how much nutrient, how much bacteria, and how much oxygen requirement was in reactor 1. We use ammonium chloride as a nitrogen source, and we use potassium dihydrogen phosphate for phosphorus source. And the amount of nitrogen or ammonium chloride was determined as 0.525 milligram. And the amount of potassium dihydrogen phosphate was determined as 0.159 milligram. And we added 5 milligram of powdered bacteria to reactor 1. And we also added 5 milligram of bacteria monthly as a maintenance dose. And again, the oxygen required for reactor 1 to biodegrade toluene was determined as 15.6 milligram. And this slide shows the toluene removal results. And in both reactors, the influent toluene concentration was 5 milligram per liter. And the reactors were run for 44 days. And after the 44 days of operation, the removal rates for reactor 1 was 13.9% only. So the initial toluene was 5 ppm and the final toluene was 4.304 ppm. So there was only 13.9% removal efficiency. But in reactor 1, which was used as a biostimulation and bioaugmentation permeable reactive barrier, the final toluene concentration was 0.0239 ppm, which gives us 99.5% removal, which was very high. And I should also remind you that the World Health Organization says that the maximum toluene concentration in groundwater should be less than 0.7 ppm. So in this case, reactor 1 provided better results compared to reactor 2. And again, the efficiency of biodegradation was the highest when the biostimulation and bioaugmentation processes were combined in reactor 1. Let's move to the discussion part. If we just use bioaugmentation, which means just adding microorganisms, it is not effective to remove the contaminants. You have to combine it with biostimulation as well. So that means you have to both add nitrogen and phosphorus and also microorganisms to these permeable reactive barriers to get a better results. And because cost of pump and treat for groundwater is very expensive and it will take a very long time, that's why these in-situ permeable reactive barriers are very reliable. And when they are very reliable and effective if you combine biostimulation and bioaugmentation processes together. And our study showed that combining biostimulation and bioaugmentation has a higher effect on biodegradation compared to natural attenuation process, which is reactor 2, natural attenuation. We did not add any oxygen, we didn't add any nutrients, and we did not add any microorganisms. So biostimulation and bioaugmentation process, combined process is much effective compared to natural attenuation. And this study assessed the effectiveness of bioaugmentation combined with biostimulation and bioaugmentation for a freshly toluene contaminated water. So we just tested toluene, but again, this process can be tested for different contaminants like benzene, PCE, TCE, and other hydrocarbons. Conclusions, our study confirmed that it is possible to enhance biodegradation of toluene in water by using permeable reactive barriers with the process of bioaugmentation and biostimulation combined. And as microorganisms, we use alkanivorax. That's the name of the bacteria responsible for hydrocarbon biodegradation. And this study was run for 44 days, and it was enough to reduce the amount of toluene in water more than 99%. And the study highlighted the importance of in-situ groundwater treatment combined with bioaugmentation and biostimulation as a suitable strategy. Thank you very much for listening to our presentation.